Chemistry involves a large number of calculations, whether we're trying to figure out the amount of a starting material to use for a reaction, or whether we're trying to figure out the concentration of a solution. And as a result, it's necessary for us to know how to keep track of our units during a calculation. Maybe the reported density is given in SI units of kilograms per meter cubed, but we want to be able to convert it to grams per milliliter or grams per centimeter cubed. We need to be able to keep track of our units. And so that's where something known as dimensional analysis comes in. This is essentially just a way of keeping track of our units during calculations. And it turns out that units can be multiplied together or divided just like numerical values are. So if we take a given unit here and we multiply it by some fraction that is a desired unit over a given unit, if we multiply this just like numbers, we would have given unit times desired unit in the numerator and given unit in the bottom at the denominator. And so given unit would simply cancel out and we would be left with the desired unit. And that's essentially just how we do most of our calculations and how we keep track of units and multiply them together and cancel them. So let's just take a practical example. If I am trying to determine the number of centimeters of a measurement that turns out to be 8.5 inches, I can multiply by 2.54 centimeters over 1 inch. I will have inches in the numerator and inches in the denominator, and those will cancel and leave me with my desired unit of centimeters. Now, this central fraction here, or the fraction up above, is something that's known as a conversion factor. That's something that allows me to convert from my given unit to my desired unit. Conversion factors are simply equalities. Any equality is a conversion factor. So I know that 2.54 centimeters is equal to 1 inch. That is an equality. And so anytime that I have some numerical value with some unit that is equal to some other numerical value with some other unit, anytime I have that equality, I can write that as a conversion factor, and I can write it however I need it to be. I can write it with the A unit on top, or I can write it with the A unit on bottom. But anytime that I have any equality, whether it's the number of seconds in a minute, or if it's the amount of feet in a mile, or the number of centimeters in an inch, any equality can be written as a conversion factor. And I will write it in such a way such as to cancel the units that I do not want and leave me with the units that I want. So when I do unit conversions, whenever I'm trying to take one value that has one set of units and convert it to some other unit value, the way that I set up these processes looks something like this. I'll always start with the initial value, the value that you are given in the top left. So you start here on the left, it's at the top, and then we're going to arrange conversion factors. And how many conversion factors we need may depend on just how many we know that are involved between getting between the unit that we're given and here this final value. I want this last conversion factor 4 in this generic example, to have the units that I want at the end, because my initial value units should cancel with the units of the bottom part of conversion factor 1. The units for the top part of conversion factor 2 should cancel with the units of conversion factor 2. This conversion factor 1 and the denominator of conversion factor 2, and then the numerator of conversion factor 2, those units should cancel with the denominator of conversion factor 3, and so on and so forth, so that the last one that I'm left with is conversion factor number 4. Again, as we just said, a conversion factor is any equality, and I can write it as I need with the unit A on top or the unit A on bottom as needed. Undesired units have to cancel. You can't be left with any undesired units that don't cancel. Your final value has to only have the final units. Let's work through a specific example here. Let's convert 12.2 feet into centimeters. Well, the value that I'm given is 12.2 feet. So that one goes in my top left. I write that in the numerator. I can just write it over 1 as the denominator, so just so that it fits in the same category. Now is when my conversion factors would come in. I don't know a conversion factor. I don't know an equality that relates feet to centimeters right away, but I do know equalities that relate feet to inches. So there is 12 inches in 1 foot. And I know that there are 2.54 centimeters in 1 inch. So there are 2 conversion factors there, feet to inches. And I can write that so that the inches is on top and the feet are on bottom, so that the feet will cancel. And then I know inches to centimeters, or centimeters to inches. I write centimeters on top and inches on the bottom, so that the inches cancel and the feet cancel. This now, if I multiply it through, I cancel out the feet, I cancel out the inches, and the only unit that I'm left with is centimeters. Now, I'll come out with some value initially, 371.856 centimeters, but I have to go back and remember my significant figures rules. This is a multiplication and division problem. My initial value has 3 significant figures. So what number of significant figures does my final value have? Well, it will also have 3, so I will round this to 372 centimeters. You might wonder, why does it have 3 when 12 only has 2, or 1 only has 1? Well, that's where we have one thing we have to keep in mind. Conversion factors that are exact values have no impact on the number of significant figures, because there's no uncertainty associated with those values. There is exactly 12 inches in 1 foot. That's the definition of a foot. There are exactly 2.54 centimeters in 1 inch. That is a definition. There are exactly 12 eggs in a dozen. That's a definition. That's not an uncertain number. There's no uncertainty associated with it. It's not a measured value. It's an exact value. And so it has no impact on the overall number of significant figures, and we can simply base that off of the number of significant figures that we started with. However, conversion factors that are measured values, such as density is a measured value, that would impact the number of significant figures. So if I were doing a calculation that involved density, I would then have to pay attention to the number of significant figures in that value. Let's do another example. What is 0.00124 kilograms in ounces? Well, first, again, I put kilograms in the top left, and then I look at my conversion factors, equalities, whatever they happen to be. In the back of your book, you will find equalities and conversion factors that relate many different units. Ounces and kilograms are both units of mass. And I don't know a direct conversion between ounces and kilograms, but I do know a conversion between kilograms and pounds, and between ounces and pounds. And so I can take these equalities and I will set them up. I will figure out which unit I want to end up with, ounces at the end. And I will first put a conversion factor at the beginning that relates the unit that I start with to a different unit. So here I'll relate kilograms to pounds. Kilograms goes on the bottom, pounds goes on the top, so that the kilograms will cancel. Then I put ounces and pounds, that equality. There's 16 ounces in 1 pound. So 16 ounces will go on the top, so that my desired unit, which is ounces, is the last one. It stays on the top. Pounds goes on the bottom, so that it cancels with the other pound. And I multiply through and I come out with the number of ounces. I again have to keep track of the number of significant figures. I'm limited to 3 here because I start out with 3. 16 ounces in 1 pound is an exact value. Now, 2.2046 pounds in 1 kilogram, that's not exact. That's not an exact conversion, but it has a larger number of significant figures than the one I started with. I can also write this in scientific notation. So you may want to go back and review how to do scientific notation, but I could write this as 4.37 times 10 to the -2 ounces. Now, What if I'm doing a conversion that involves a unit that has a power, something like meters cubed, or in this case, inches cubed? So a flask contains 156.3 inches cubed. That's its volume. What is this value in liters? Well, the main thing here is that undesired units have to cancel completely. I can't cancel a unit with a power with just a unit without a unit without a power unless sorry, say that again. I cannot cancel a unit with a power with a unit that does not have a power. So what I would do first is I'll take my a cubed unit, and it needs to have a cubed unit in the conversion factor in order to be able to cancel completely. So if I can set this all up in something in some way like this. I'll take 156.3 inches cubed. I don't know any conversion factors that involve inches cubed, but I do know conversion factors that involved inches. So inches to centimeters here, for example, 2.54 centimeters in 1 inch. And I will take that conversion factor and I will cube the whole thing. This cubes the number inside and the unit. So I will end up with 2.54 times 2.54 times 2.54 centimeters times centimeters times centimeters gets me centimeters cubed over 1 times 1 times 1 is just 1 times inches times inches times inches, that's inches cubed. And then I will take that value. That will now leave me with inches cubed on the bottom, which can cancel with the inches cubed here. That now leaves me with centimeters cubed. Now, I do also know a conversion factor that involves centimeters cubed, and that's the conversion between milliliters and centimeters cubed. So 1 milliliter is the same as 1 centimeter cubed, so I put 1 centimeter cubed on the bottom, 1 milliliter on top. Those can now cancel. Now I've got milliliters, and I simply have to convert between milliliters and liters. That's a simple metric system prefix unit conversion. 1 milliliter is 1/1000th of a liter. So there are 1,000 milliliters in a liter. I multiply through, I check my number of starting significant figures, put that at the end, round to the appropriate number, and I come out with an answer there. Additionally, I can have cases where maybe my unit is squared. In this case, the area of a circle is 21 millimeters squared. What's that area in feet squared? Well, again, 21 millimeters squared. I start out with that value in the top left. I convert from, I don't know a conversion between millimeters and feet. What I do know is conversion between the English system and the metric system is primarily the inches to centimeters. So on the one hand, I will convert from my millimeters up to centimeters. And then once I've converted over to inches, then I can convert to feet. And I use all of the equalities that I know. There's 10 millimeters in a centimeter. I am going to have to square that conversion factor in order to make sure that my millimeters are squared. That will make my centimeters squared. So my millimeter squared can cancel. This also squares the number in the bottom here. So it's going to be 10 times 10 at the bottom. I can then convert between inches and centimeters, but I have to square that conversion factor as well. And I can convert between inches and feet, and I have to square that as well so that my final unit is feet squared and so that my previous units all cancel. And then of course I keep track of my significant figures as I've done all along. Lastly, it's important to talk just briefly about conversions that involve density, because density itself is also just another conversion factor. It's saying, if we take, for example, this problem where I have what's the mass in kilograms of a gold sphere that has a volume of 2.26 milliliters. And I'm given the density here. Density is 19.3 grams per centimeter cubed. Anytime that you have a unit that's over another unit, you can set those two, what that means is there's an equality there. 19.3 grams is equal to 1 centimeter cubed. That's what that means. Anytime you have unit over another unit, it means the numerator with its unit is equal to the denominator with its unit. The denominator in most cases is just 1. So 19.3 grams is equal to 1 cubic centimeter. So I can start with my volume, put it here in the top left, and then convert from milliliters to centimeters cubed. This now gets me to a unit that is now related to the density. And so I can use this. I'll set it just as it is, 19.3 grams on top over 1 centimeter cubed on the bottom. That cancels my centimeters cubed. Leaves me with grams, but I've been asked for the mass in kilograms, so then I simply use my conversion between grams and kilograms. Again, units on the bottom so that they cancel, and I'm left only with the final unit that I want. And then I can make sure to report my final answer to the number, to the correct number of significant figures. Now, density is a measured value, so it does impact the number of significant figures. In this case, both my starting value and the density have 3 significant figures, so I will only report my answer to 3 significant figures. One more example. What's the density of benzene at 15 degrees Celsius is given as 0.8787 grams per milliliter. Calculate the mass of 0.1500 liters of benzene at this temperature. This is my given value, right here, the 0.1500 liters. This density is my conversion factor, or one of them, and I will need another one. So first I start by putting the given value in the top left. I have to convert from liters to milliliters so that I can then use my density. So I'll take 1,000 milliliters per 1 liter. That cancels the liters. Now I can use my density, grams per milliliter, cancel the milliliters, multiply through, and then I just have to make sure I only report this to 4 significant figures. Very last example using density. What's the volume of a titanium cube that has a mass of 4.56 kilograms? And I'm given the density. This is my given value, the 4.56 kilograms. Set that in the top left. Kilograms, I will convert that first to grams now so that I can then use my density. And in this case, remember 4.51 grams is equal to 1 centimeter cubed. I can write that however I want. It doesn't have to be grams on top and centimeters cubed on the bottom. In this case, I want grams on bottom so that it will cancel with the other grams here and centimeters cubed on top. You multiply through, report to the correct number of significant figures, and we come out with our answer. So just to summarize the chapter 1 briefly, we've talked about definitions of chemistry and matter, classifications of the properties of matter, and physical and chemical properties and changes. We spent a little bit of time talking about the standard units of measurement, and then uncertainty, precision, and significant figures and how we keep track of that. Now finally we finished up with dimensional analysis, how we convert from different units, how we do calculations and keep track of the units involved. So with that, I'll leave you just with this example of why it's really important to keep track of our units and keep track of our significant figures and precision all along.